let's do lecture 7.1, solving for the state space response. So remember, we have this state space model and we're trying to solve it directly now. Instead of converting it into an input-output differential equation and then solving it, we're trying to solve it directly. And we're going to find that it's not so bad, really, but there are a couple things we're going to need along the way that take a little bit of work. So let's figure those out. So we're going to solve the state equation for the state response x of t. So that'll be the first thing we're solving for. And substitute this into the output equation for the output response y of t. So once we have x, y sort of comes along for free. So that's the focus is to solve the state equation, the differential equation. So the state response. The state equation can be solved by a synthesis of familiar techniques as follows. So remember what it looks like. It looks like this, right? This is our state equation. dx dt equals ax plus bu. The first step is we're going to subtract the ax term from both sides, like in algebra, but with linear algebra. It's amazing. I know. Subtract ax from both sides, and we get this expression in 7.3. An integrating factor would be clutch, but what should it be? Integrating factor might be something that you're a little rusty on. It's something that was brought to you by differential equations class. And you might have seen it in this context. I'm gonna do it on the sidebar here. So imagine you had a scalar equation, dx dt minus scalar a x equals scalar b u, all scalar. Using an integrating factor, one might attempt to solve this equation by multiplying both sides of the equation by e to the minus a t. And so the first term, so we'll distribute it, so dx dt. And the next term is going to be minus e to the minus at ax. The right-hand side is going to be e to the minus at bu. So we just multiplied everything by e to the minus at. Then we can recognize that this left-hand side is actually the derivative of another term, the time derivative of, so d dt, a single term, which is e to the minus at x. And the right-hand side would stay the same. So if you take this is the product rule, right? So say we took the derivative of the x term first, when we do the product rule, so it would be dx dt e to the minus at. And then we take the derivative of the exponential term and we add it. So plus e to the minus at is the derivative of e to the minus at. But then you have the chain rule, right? Because you got this expression up there. So the derivative of that is negative a. So get a negative and an a popping out, and then the x is not differentiated. So this is an integrating factor that we've identified. Oh, this is just the derivative of this term. And then you can split off the two differentials, and you get d e to the minus at x equals e to the minus at bu dt. Now you can integrate both sides and solve for x. Okay, so that's what we did. So this is what we would do with an integrating factor. You would do integral from 0 to t, for instance, of d e to the minus a tau. You'd need to use a dummy variable for integration purposes. I'm going to pop that over just a bit. X of tau equals integral from 0 to t of this term here, so e to the minus a tau b u of tau d tau. The integral of this differential is just this term right here evaluated at time equals t, evaluated at tau equals t, and then evaluate minus evaluated at time equals 0. So we would get e to the minus a t x of t minus e to the 0, which is just 1, right? X of 0, the initial condition, equals the same right-hand side, okay? And then you would just simply solve for x of t. So just add x of 0 to both sides, and then multiply e to the at to both sides, and you'd get your solution, x of t. So that's how we used integrating factors before. Is that like ringing some bells, maybe?
A little bit, yeah.
A little bit. Some like faint bells back there. By the way, if anybody likes good mystery books, The 9 Tailors is a good one. You guys familiar with that? Dorothy Sayers? It's old. So it's a classic. Has bells in it. That's how it was related to this. Everything is related. Okay? All right. Good. So we've got that like in the back of our minds, right? So this is not what we have. We have a vector equation, but the scalar equation usage of an integrating factor is in the back of our minds as we approach this new problem. So we arranged this, and we have something that looks a lot like this expression here, but it's in vector form. So if we can kind of do something analogous to that, we'll be good. That's exactly what we'll do. So this looks analogous to a scalar ODE that would use the natural exponential. So I'm going to use, in most of the lecture, I'm going to use exp as the exponential function because we're going to have a lot of them show up, and it's a little bit hard to see the exponents when you have a lot of exponentials in your equation. So I'm just going to use this exp notation, just the same as good old-fashioned e to the whatever, okay? But we have a vector ODE. We need a matrix version of the exponential is what we need. So recall that a series definition of the scalar exponential function, the good old-fashioned exponential function, is the exponential of z, some complex number, equals the sum from k equals 0 to infinity of 1 over k factorial z to the k. That's the good old-fashioned series definition, or a series definition of the exponential. So you've learned this in like calculus 2, I think, when you guys did like series transcendental functions. Yeah. So we define the matrix exponential. So we're going to use all the math. We like using all the math. It's paying off. Differential equations, linear algebra, calculus 2, all in one lecture. What an amazing thing. Isn't that great? Okay, So we define the matrix exponential to be analogous. We're going to use the same symbol, so exp. You'll also see the usage of little e as a matrix exponential. It's just the context of what is in the exponent. If there's a matrix in the exponent, you know it's a matrix exponential. Okay. Good. So for some n by n complex matrix Z, the exponential of Z is the sum. So it's the same exact sum, same exact 1 over k factorial. But this time, instead of just having a scalar complex number raised to the k power, we have a matrix, complex matrix raised to the kth power. Complex matrix is a matrix that has complex values in the as elements. So we've got this exponential of a matrix. So if you take a matrix, just to like give us a little bit of a memory of how you would take a power of a matrix. So if you wanted to raise a matrix to the second power, that's just the matrix times itself. So if you raise it to the kth power, you're going to multiply it by itself k times. So that's our definition, because why not? I mean, it's analogous to the scalar exponential. There's no reason not to give it a shot. So for the hell of it, let's see if the matrix exponential, where we put in the A matrix, so negative AT, put in the A matrix from our state equation, works as an integrating factor, if for no other reason than it was constructed to be a sort of matrix analog of the scalar exponential e to the negative AT, which would work for the scalar case. So we're gonna give it a shot because it's like very analogous. And this is actually how a lot of stuff gets discovered in math, is that people are like, they see a sort of similarity or they try something from another area on a new area and they see if it works. And a lot of times it does work. So in this case, this would be such a great lecture if in the end it didn't work. You guys are all expecting it to work, right? Plot twist, doesn't work, and then we just end the lecture. That would be so great. Oh, okay. I'm going to do that sometime. But like with something that actually doesn't work, because this actually does work. So good. So we're going to pre-multiply, or left multiply sometimes it's called, 7.3 on both sides. So 7.3, to recall, is this version of the state equation that we have rearranged a little bit. So we're going to multiply both sides by our matrix exponential and see if we can get something cool to happen. So we have the matrix exponential of negative AT, multiplying the first term, which is dx dt, right? And then the next term is, once again, we'll have another matrix exponential of negative AT. And that one will be multiplying the other term, which was AX. So it's still going to be AX. And the right-hand side is also going to pick up a matrix exponential of negative AT. And it will multiply BU. Cool. So we're going to do this step where we recognize that this left-hand side has two terms that are two terms from a product rule application of the derivative, the time derivative. So on this left-hand side, we're going to have dt of it's going to be is the exponential of negative AT and then x. Okay. So that'll be the left-hand side, and we'll leave the right-hand side the same in this step. So let's check what we just did. So if you take the time derivative, let's do this term first. So in the product rule, we take the derivative of one term and we leave the other term alone, and then we add the derivative of the term we left alone with the term that we differentiated the first time. So that's the product rule. So let's differentiate x the first time, so dx dt. We left the matrix exponential alone, so that was this term. The other one's a little bit more tricky, so we take the derivative of the matrix exponential. We haven't really explored what the derivative of a matrix exponential would look like and how the product rule would apply, or pardon, the chain rule would apply. But we'll put this as a little bit of a like an exercise for ourselves. So exercise, prove that if you take the time derivative of the matrix exponential, so of negative at, that you're going to get negative exponential, I'm going to put it on the next line, it's a little bit too cramped, negative exponential of negative at times a. So that would be something that we need to prove that. It makes sense. It's very analogous to what the derivative of the scalar case is, but the order of the matrix multiplication could be important in this case because we have matrices and not scalar multiplication, and so it is important to go ahead and work out what the derivative is. And I'm saying this is true. And you can go back to the series definition of the matrix exponential and prove that it's true. So in any case, I'm going to just say this is an exercise to prove that, but I'll posit that it is true, and we can write this expression. Great. So rearranging and integrating over the time interval 0 to t. So let's rearrange like we did in the scalar case, and let's rearrange our differentials to be on different sides. So we're left with d exponential of negative at x on the left-hand side, and on the right-hand side we're going to have what was left over there, exponential of negative at bu dt. Okay. This can be rewritten in an integral form, so we can integrate both sides from 0 to t like we did before. So if we do that, we're going to get the integral from 0 to t of d exponential of negative a tau. We need to use the dummy variable of integration here, and x of tau. It's actually, I mean, we often ignore the subtlety of needing to use the dummy variable of integration. We just put in t. But that actually gets pretty confusing when you have a definite integral from 0 to t. It's best to just go ahead and use that dummy variable in there. The other side has an integral that is similar, 0 to t, of exponential of negative a tau b u of tau d tau. Great. The integral on the left-hand side is easy to evaluate, just like it was in the scalar case, because we're just integrating a differential. And we evaluate the expression at tau equals t, and then we subtract out what the expression is at tau equals 0. So we get exponential of negative at x of t, or we've been typically just saying x when we mean x of t, right? So we can leave that off if we want. Minus, so I'm going to say that the matrix exponential of 0, with argument of 0, gives you the identity matrix. Just like e to the 0, the scalar version gives you 1, the matrix exponential gives you 0, or gives you the identity matrix. And I'm just going to state that without proof. And then I evaluate x at time equals 0. The right-hand side stays the same, so we can just rewrite it. It's kind of a large tau. It's a beach towel. I like it. Puns are the best. This last expression can be solved for x, the state response solution. So we've got x all by itself here pretty much. We can add x of 0 to both sides, get rid of this term. Then we can multiply both sides by the matrix exponential of at, which I'll posit is the inverse of the exponential of negative at, and solve for x. But before we do this, let's define the matrix function called the state transition matrix, phi, to be the matrix valued function, the matrix exponential of at. Okay? So when we multiply both sides by exponential of at, this one's going to go away, and we're going to get this exponential of at on the right-hand side, and that's going to show up twice, and we're going to call that capital phi, the state transition matrix. And it's going to be a key matrix, and that's why we're giving it a special name. So if we substitute in phi and solve, then we get that the solution for x, so this is our state solution, the solution we've been looking for all this time, is the state transition matrix multiplying the initial condition plus state transition matrix multiplying this integral, okay? And which also includes the state transition matrix. If you would like, you can actually combine these two phis together, and that's what is being done in the second version. So either version here is pretty good. You can use either version. They're both pretty useful. There's aren't like significant advantages to one versus the other. Occasionally one makes more sense than the other in a given problem. So first thing to note here is that we have our solution. Boom, star. That's great. We have the solution for the state as a function of time for every single state equation. So we have a solution. So like we solved that differential equation once and for all, right? We don't have to solve it every time we encounter it, which we had to do for the case of the input-output ODEs, unless we use the tables and all that. So this is a pretty powerful result. It's like it's the solution. When you look at this, you say, oh, okay, B. I know my B matrix. I have my input, which is always given. So I can't integrate this directly until I know what the form of the input function is. But if I know what the form of the input function is for a given problem, which I will for a given problem, I can do this integral. The only thing that's unknown here is the state transition matrix when you start, which is defined as this matrix exponential, which is defined as Oh, I passed it. Defined as something. There it is. It's just right above there. I don't know why I was like, oh, matrix exponential. There it is. This guy, 7, 4. That's the definition. So a naive way to think about the matrix exponential, which is incorrect, is to say, oh, it's just a scalar like in the matrix, and so you would just put e to the whatever term in the A matrix and you'd be good to go. That does not actually work out that way. It does in one special case, and we'll explore when that is. But really the definition is this, and you have to go back to that when you construct your matrix exponential. So finding that state transition matrix, which is a matrix exponential, turns out to be the main work of solving the state equation. Because if you have that, you essentially just plug it into this solution of equation 7, 7. You have to do some integration over your input, but that's all you need to do, and you have your solution. So state transition matrix becomes very key. Computing that matrix exponential becomes very key. And right now, the only tool we have is the definition of the state transition matrix and the definition of the matrix exponential, which is a series definition. And if you guys are remembering your Calculus 2, where you guys were doing series definitions of transcendental functions, they can get a little bit, they can be a little bit tough to work with, the definitions. You have to recognize patterns in series of terms that arise to know like what the function is that you're dealing with. It's kind of tricky. So we're going to get away from that in 2 lectures. We're going to introduce a new way of computing the state transition matrix. But the definition is good to be familiar with. So that's the first thing to do, is to become familiar with the definition of the state transition matrix. So let's look at another aspect that's important to remember here is that the first term, so I'll actually highlight on the second version of the equation. It doesn't really matter which one. The first term here is the free response, because it's due to the initial conditions only. And the second term is the forced response. Because it depends on the input only. So the solution is nice because it gives us those 2 components of our solution separately. And we can see that free and forced response solutions just spontaneously emerge in our solution. And if we want just the free response, so we want the input to be 0, we can simply ignore the forced response part. If we want the forced response and we don't want to know what happens with initial conditions, we just ignore the free response part, and we're off to the races. So good. Let's look a little bit deeper at the state transition matrix. So it wound up being a key aspect of the response, which is why we call it that. We call it the state transition matrix because it helps transition the state through time. And I mean, we can think of it that way at least, right? So we used 2 of its properties in the matrix exponential form during that derivation. The initial value, which is to say that phi of 0 is equal to the identity matrix. I said, oh, if you take the matrix exponential of 0, you get the identity matrix. You can go back to the series definition and see that pretty easily. That one's pretty easy to see. We also use the fact that the inverse is just changing the argument, and this is because it's an exponential. In an exponential, if you have like e to the t as your function, and you want the inverse of that, you just change the sign on the exponent, right? E to the negative t gets you the inverse. The same is true for the matrix exponential. There's a third property we might call the bootstrapping property. It's not given a name in the Rao and Wormley text, but I think that's a good way of describing it. For time intervals delta t, if you want to know what the state transition matrix is for some time that is the sum of a bunch of these incremental times, you can simply use maybe previously computed state transition matrix times and multiply them together. This is going to be specifically interesting for a problem in your homework that you're going to be seeing. This bootstrapping property will help you. It allows one to compute the state transition matrix incrementally from one previously computed. A final property we'll consider is the special case of a diagonal A matrix with diagonal elements being A11, A22 to ANN, which yields a diagonal state transition matrix. So this is the only one where like our naive just plugging into the form of it is going to actually be true. So if we do the exponential of well, so I guess I'm doing phi, so I'll do that. I'll just say phi of t equals, by definition, exponential of at. And just to like make sure that we remember this, in this specific instance, it's only for a diagonal A, right? So this is not a formula that generally applies. It's only when A is diagonal, okay, that this is true. We have e to the A11 t, e to the A22 t along the diagonal, and then all the way down to e to the ANN t. And all of the off diagonal terms are 0. So this is the only one that we actually have like an easy result for. If you have a diagonal A matrix, you just have a nice diagonal state transition matrix. And we're going to use this property in lecture 7.3. Okay? And it's going to be very convenient for deriving the state transition matrix for a given problem. Effectively, what we're going to do is we're going to change bases in our state equation so that the A matrix is diagonal, which you can do. And then we're going to compute phi, and then we're going to transform that into our original basis. That's approximately what we're going to do. You're going to need to know the eigenvalues and eigenvectors along the way. That's what the next lecture is about. Okay, so for now, we must rely on the definition of phi from equation 7.6 and the series definition of the matrix exponential from equation 7.4 to find what the state transition matrix is, unless we already have this nice form. It's already A is exponential, and then we can just use this formula. But otherwise, we have to use the series definition. This requires us to first derive the first several terms of the series solution and attempt to divine the corresponding scalar exponential series, which is a rather tedious task. And you have a couple homework problems where you do this, and the Rowland Wormley text has a worked out example of how to do this. It's pretty tedious, but it's worth going through to give you like a feel for the definition. Other than to familiarize ourselves with the definition through exercises, we prefer the derivation method of lecture 7.3. So typically we're not going to use the definition to find phi, but we will when we first get started, just to get familiar with it, and then we'll introduce a new way. Okay, the output response. Y of t requires little additional solution. Assuming that we've already solved for the state response x, the output is given by the output equation, which is just this, right? If we know x, u is always given. We know the output. Great. So we can, if we want, just plug and chug into that equation if we have our x solution. And that's all I did here in equation 7.10, is I just plugged in the solution for x and expanded it out. So that's the output response. So once you have the state response, you have the output response. It comes along pretty much for free. with a couple of matrix multiplications. That's it. All right. Very good. Any questions on that? Okay.